Hello. So we're continuing chapter 3 with 3.2 polynomial functions and their graphs. And again, if you um, or you're welcome to, of course, pause the video at any point and to catch up with the writing and all the notes and everything. And at any point, if you've got any questions about it, just please don't hesitate to contact me. All right, so we're going to go ahead and define a polynomial function. So n is a non-negative integer, and then we've got a sub n, a sub n minus 1, and all the way to a sub 2, a sub 1, and a sub 0. All of these are real numbers with a sub n does not equal 0. So the function defined by f of x, a times n, so that's the coefficient, x to the power of n plus and so on. So this is called a polynomial function of degree n, and the n comes from the exponent. We've talked about this already a little bit. So the number a sub n is the coefficient of the variable to the highest power, and that is called the leading coefficient. So the numbers in front of the x's are the coefficients, and the number that the coefficient of the variable to the highest power is called the leading coefficient. Okay, so next we're going to look at graphs of polynomial functions, smooth and continuous, and define what that means. So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. And notice that it says degree 2, so this includes quadratic functions. So by smooth, we mean that the graphs contain only rounded curves with no sharp corners. And by continuous, we mean that the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. Okay, next we're going to look at the end behavior of polynomial functions. So the behavior of the graph of a function to the far left or the far right is called its end behavior. So this is what's happening far left and far right. So for example, if we have a graph like this, the end behavior would be what's happening here and what's happening here. Okay, so although the graph of a polynomial function may have intervals where it increases or decreases, that graph will eventually rise or fall without bound as it moves far to the left or far to the right. So rise or fall without bound. So the sign of the leading coefficient and the degree of the polynomial function reveal its end behavior. And again, the leading coefficient, remember, is the a sub n, and the degree is n. So, for example, if we take just our plane, I'm just going to draw two coordinate planes here. If we do just a straight line, actually, let me draw it through the origin like this. So this is y equals x, right? that is to the power of 1. We don't have a degree here, but it is. So this, if we look at this one, or when we're talking about the sign, if I draw one like this, we all know that that is a downhill. So negative x to the power of 1. Now we have a negative leading coefficient, and for the y equals x to the power of 1, we have a um, positive coefficient. So we can see where, the ends are going. So we can actually, what we can do is we can start with these simple ones. We know that this one here, it falls to the left and rises to the right. And we know that if it's a negative x, it rises to the left and falls to the right. If we graph a quadratic function like this one, y equals x squared, well, again, so now our degree is 2. The ends are going the same way. So with this one, both are rising to the far left and to the far right. If we do a downward, so y equals, and we know that that's going to be a negative. We talked about it in 3.1. We can see that both ends are falling downward. So there's a little bit of a, so when we've got positive, they're both, or I'm sorry, not positive. When we have an even number, which 2 is an even number, 2, 4, 6, 8, the ends are going to go the same way. When we have an odd, like 1, the ends are going to go different ways. And then it depends on if it is a positive or negative, which way they're going. Okay, so on this next page, we're going to look at the leading coefficient test, which we already a little bit looked at. So as x increases or decreases without bound, the graph of the polynomial function, f of x, eventually rises or falls. So in particular, the sign of the leading coefficient and the degree n of the polynomial function reveal its end behavior. So we're going to look at first when n is odd. So that is our 1, 3, 5, 7, and so on. So for the odd ones, if the leading coefficient is positive and graph falls to the left and rises to the right. Oops, that's too big. I can't fit 4 graphs that big here. Okay, here we go. So odd, we just looked at odd right here. 1 is an odd. So if the leading coefficient is positive, so a sub n is greater than 0, we know if we look at this one right here, it falls to the left and rises to the right. So this is our far left, and this is our, sorry, not far left, falls left, and rises right. Again, this is odd degree and positive leading coefficient. Okay, next one is going to be, we're still talking about odd odd degree. That has not changed. What has changed is that leading coefficient is negative now. So if we look at this one right here, what happened when the leading coefficient was negative with an odd degree, it rises to the left. So rises left and falls right. So this is leading coefficient is negative, so less than 0. So it's odd degree, negative, leading coefficient. Okay, now we're going to go to even degrees. So n is even, so 2, 4, 6, 8, and so on. We're first going to again start with leading coefficient is positive. So a sub n is greater than 0, sorry. If we look at this one right here, the n is even, our degree is even, and the leading coefficient is positive. It goes up on both sides. So rises left and rises right. This is the even degree, 2, 4, 6, 8, and a positive leading coefficient. And remember, we're not talking about what's happening in the middle. We're only talking about those ends, like what is happening at the end. Okay, next one is going to be leading coefficient is negative, so our a sub n is going to be less than 0. So if we look at the this one right here, well, it's a downward. So both ends fall. So falls left and falls right. And this is the even degree and negative leading coefficient. Okay, so let's see how we use this, the leading coefficient. So we have use the leading coefficient test to determine the end behavior of the graph f of x equals x to the power of 4 minus 4x squared. So we've got our function is x to the power of 4 minus 4x squared. Our degree is 4, which is even. So that comes from the exponent, the highest exponent. Our leading coefficient, there's no number, so it's going to be a 1. Leading coefficient is right here. It is the understood 1. That is greater than 0, which means that it is positive. So even and positive. Even, oops, that's a, I did not mean to underline that. It was this one, even and positive. So rises left and rises right. So when we graph this, or sketch it, so rises left and rises right. The graph rises to the left and to the right. So that is your answer. Now, it can, so it doesn't matter what happens down here. It does look something like this, a little bit more symmetric, but something similar to that. But again, this question was only about the end behavior. We don't have to worry about what happens in between the ends at this point. We'll look at it in a little bit. And this will tell us more about what happens in the end when we're looking at zeros of polynomial functions. So if f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f of x. These values of x are the roots or the solutions of the polynomial function f of x equals 0. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. So let's look at an example. We're going to go ahead and find the zeros. Remember, the zeros is the same thing as the roots as the solutions. There's many names for these. This one is asking to find all zeros, but if you're being asked to find all the roots or all the solutions, you're doing the exact same thing. So what we need to do is set the function to equal 0. So x cubed plus 2x squared minus 4x minus 8 equals 0. Now, I'm looking at this. It is to the power of 3. We can't factor it, or we are going to factor it, but what we're going to do is we're going to factor it by grouping. So we're grouping x cubed plus 2x squared. Common factor for those is x squared. X is left from the x cubed when we take out x squared, and plus 2 is left from the 2x squared when we take out the x squared. For negative 4x minus 8, we're going to take out negative 4. That's the greatest common factor for both of those. We have an x left here, and we have a plus 2 left on the other one. Now notice that x plus 2 and x plus 2 are the same, so we can actually use x plus 2 is one of the factors. Those two have to be the same for us to rewrite it. The other factor is going to be x squared minus 4 equals 0. Okay, now we can use the 0 product rule. So x plus 2 equals 0 and x squared minus 4 equals 0. Subtracting 2, moving it to the other side, we get x equals negative 2. Here we're adding 4. So x squared equals 4. Positive and negative taking the square root. So x equals positive and negative 2. Well, we've got 2 times negative 2. So we're only going to write it once. So the zeros of this f of x are negative 2 and 2. Sometimes we might get, or usually if we have, like this one is a degree of 3, we should have three different zeros. Well, we do, because this is 1 and here's 2, but 1 is the same. And we'll talk about what happens actually next when we have something like this. So we're going to next talk about multiplicity and x-intercepts. So if R is a 0 of even multiplicity, then the graph touches the x-axis and turns around at R. If R is a 0 of odd multiplicity, then the graph crosses the x-axis at R. Regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with multiplicity. Okay, so let's look at finding zeros and their multiplicities. The example here. So find the zeros of f of x. and give the multiplicities of each zero. State whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. Okay, this one here, so we have negative 4 x plus half squared x minus 5 cubed equals 0. What we're going to do is we're going to take out that first part, negative 4 x plus half squared equals 0. So we're using the zero product rule again. Now, if we divide negative by negative 4, this is going to be a 0. So that negative 4 is kind of ignored here. Now, taking a square root, and there's only to cancel out the squared, and 0 is only a 0. There's not a positive and negative 0. It's only 0. So now when we move the half to the other side, we get x equals negative half. So x equals negative half is a 0 of multiplicity and the multiplicity is right here. So it's the exponent that tells us what the multiplicity of this 0 is. So it is multiplicity of 2. So that means that this is even. So when we go back and look at even multiplicity touches the x-axis and turns around. So the graph touches the x-axis at x equals negative half and turns back. So let's look at sketching wise. Now, we're not graphing the whole thing. I'm just graphing this part right here. So what happens with it is that it, at negative half, which is here, it either it comes from up here and touches and goes back up, or it can come from down and touch and go back down. We don't know right now which one it is. Those are like two different options for it. Okay, then let's look at the other one, x minus 5 cubed. So we're going to take a cube root of both sides to cancel out the cubed here. So x minus 5 equals 0, x equals 5. So x equals 5 is a 0 of multiplicity of 3. That is odd. So the graph crosses the x-axis at 5, at x equals 5. So basically what it does is that it might go, so actually I probably should do it a little bit farther out. So if this is, for example, 5, it crosses either like this or it crosses like this. We don't know again which way it does it. But that's, at this point, that's all we know. Okay, next, the intermediate value theorem. So let f be a polynomial function with real coefficients. if f of A and f of B have opposite signs, then there is at least one value of C between A and B for which f of C equals 0. So what that means is that we have A and B, for example, here. We don't, I mean, basically, we don't need this at all. We don't know where these are in the coordinate system. But it could be, we could have them, for example, let's do the y-axis over here. Um, so if f of A is a different sign than f of B, that means that they're gonna be on opposite sides. So the graph might go like this, and this point right here is the C, where f of C equals 0. Now notice f of A is over here, so f of A is less than 0, it's a negative, and f of B over here is going to be greater than 0. So the signs are opposite. It could go the other way around as well. So we could have f of A over here and f of B over here then. They just have to be on opposite sides. So, and again, there's f of C that is a 0. I'm holding the pen somehow that it keeps erasing. So, um, equivalently, the equation f of x equals 0 has at least one real root between a and b. So that's what f of c equals 0 is. Okay, let's use this intermediate value theorem with an example. So show that the polynomial function f of x equals 3x cubed minus 10x plus 9 has a real 0 between negative 3 and negative 2. So what we're going to do is we're going to plug in negative 3. So f of negative 3, 3 times negative 3 cubed minus 10 times negative 3 plus 9, and we can plug this whole thing in the calculator. We get negative 42. Now we're going to do the same thing for negative 2. So f of negative 2 is 3 times negative 2 cubed minus 10 times negative 2 plus 9, which is 5, and it's a positive 5. So notice now that these two, one has a negative and one has a positive, so they have opposite signs. So this means that the sign change shows that the f of x has a real 0 between negative 3 and negative 2. If it did not have a negative and a positive, the opposite signs, it would not have a real 0 between. So if we kind of sketch this, it's not asked for us to sketch, but we're going to go ahead and kind of sketch it. And this is going to be interesting to sketch because of the values. So our negative, let's actually do negative 2 and 5 first. So negative 2 and 5 is going to be somewhere over here. That's negative 2 and 5. And then negative 3 and negative 42 is going to be somewhere all the way down here, probably even farther down. So what happens is that it does cross right here and then it goes somewhere. So there's that real zero. And then it probably does something like this or whatever. It doesn't matter what the rest is. We just know that between these 2 points, there's a real zero right here. Um, we just don't know what this point is. We didn't calculate that. We just know that it goes through. Okay, next thing that we're going to define are the turning points of a polynomial function. So in general, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. If we think about, for example, a quadratic function. So a quadratic function, if we have y equals x squared, it looks like this, right? It has only that one turning point. Our degree is 2, so n minus 1, 2 minus 1, there's one turning point. Now, when we graph a polynomial function, so now we're going to kind of put everything that we know together, and we're going to use that knowledge to graph it. So we're first going to use the leading coefficient test that we learned in the beginning to determine the graphs and behavior. So we're going to figure that out first. Step 2 is going to be find x-intercepts by setting f of x equals 0 and solving the resulting polynomial equation. So if there is an x-intercept at r as a result of x minus r to the power of k in the complete factorization of f of x, then if k is even, the graph touches the x-axis and turns around. If k is odd, the graph crosses the x-axis at r. If k is greater than 1, the graph flattens out near r0. Step number 3, find the y-intercept by computing f of 0. Step number 4, use symmetry if applicable to help draw the graph. So y-axis symmetry f of negative x equals f of x, and origin symmetry f of negative x equals negative f of x. And then step number 5, use the fact that maximum number of turning points of the graph is n minus 1, where n is the degree of the polynomial function, to check whether it is drawn correctly. Okay, so now we're going to use that 5-step strategy to graph f of x equals 2 times inside parentheses x plus 2 squared times x minus 3. So our very first step, let me rewrite the function here. X plus 2 squared x minus 3, there we go, is to determine the end behavior. So we're going to look at the degree. Now, notice that there's a 2 here, and this has a 1, even though it's not written as 1. There's no number, so it is that understood 1. So our degree is going to be 2 plus 1, which is 3. So make sure that if it is in this form, the function, that you're adding all the degrees, the variable degrees, so the ones that are with the x, together. Okay, our leading coefficient, this is, since it is the third degree, our leading coefficient is going to be a sub 3. That is going to be 2, which is right here in the front. That is greater than 0. So our degree is odd with a negative leading coefficient. We can go back to the very first page here. Was it the first page? Yeah, well, second page. So odd with a positive leading coefficient. So we're looking at this first one right here. So falls left, rises right. So odd ends going different directions. And we know because it's a negative that it looks like this. So there's our end behavior. Now we're going to figure out what happens in the middle, in between those ends. So step number 2 is going to be finding the x-intercepts, zeros of the function by setting f of x equals 0. So 2 parentheses x plus 2 squared times x minus 3 equals 0. Again, we don't need to worry about the 2 because that kind of divides itself out. We're just going to do x plus 2 squared equals 0 and x minus 3 equals 0. Well, this one's easy. We add a 3 and we get x equals 3. The multiplicity for this one is a 1, so it's odd, which means that it crosses. So it crosses the x-axis at x equals 3. Okay, this one here, we're going to take, oops, that was not, the square root to cancel out the squared. So x plus 2 equals 0. Again, 0 doesn't have a positive or negative. It's just 0. We're going to subtract 2, so we get x equals negative 2. Our multiplicity for this one is at 2, which is even. So that means that it touches and turns around at negative 2, 0. And this one is the 3, 0. Okay, so what we can actually start doing here is that we can start, let's graph it over here at the very end, or start sketching it here. So, hold on, what did we get? Negative 2 and 0 and 3 and 0. Negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4, 5. So, negative 2 and 0 is here, and 3 and 0 is here. And we know that it crosses, and here it doesn't. We just don't know which way it's going yet, but those are our zeros. And we know, for the first part, we know that it's the end behavior is going to be like it's going to be going up here, and then it's going to be going down here. We'll figure it out the middle part next. So next what we're going to do is find the y-intercept by computing f of 0. So we're plugging in 0 where we have x. So 2 times 0 plus 2 squared, parentheses, 0 minus 3. Okay, so 2 squared times negative 3. Well, we have a negative, so we know that this is going to be a negative. 2 times 4 is 8 times negative 3 is negative 24. So this is our y-intercept. So it's 0, negative 24. So let's sketch it over here. So 0, -24 is going to be somewhere here. This is not in the correct scale. Um, so that's our 0, -24. Let me write these -2 and 0 and 3 and 0. There we go. Okay, so now we're going to use possible symmetry to help draw the graph. So what does that mean? We're going to try to look at if there is um, y-axis symmetry or origin symmetry. So what we're going to do is we're going to see if f of -x equals f of x. So our f of x, our original is 2 times x plus 2 squared x minus 3. So we're going to see that if we plug in f of -x, if that's going to be the same. So 2 parentheses -x plus 2 squared parentheses -x minus 3. Nope. This is not the same as what we have for f of x. So these two are not same. So that means that there is no y-axis symmetry. Now we're going to see if there is origin symmetry. So we're going to see if f of -x equals -f of x. We already have calculated the f of -x. Now what we need to do is see if -f of x is the same. So -2 x plus 2. And for this one, we need to use the original one, x minus 3. Well, these two are not the same either. So that means that there is no origin symmetry. So we really, if we had the symmetry, we could kind of do something about this. We just, with this one, we really don't have it. So what we need to do is we need to calculate a couple of points here. Since we have a -2, we're going to do f of -1. So plugging in that number, 2 parentheses -1 plus 2 squared parentheses -1 minus 3. So this is going to be -8. So one of the points is -1, -8. So -1 and -8 is going to be somewhere here. Okay, so now we know that it's coming from here. The graph is coming from somewhere here. And we know that it's going to turn at -2, 0, and go back down. Okay, we already had 0 calculated. Let's do 1. So f of 1 is going to be 2 times 1 plus 2 squared 1 minus 3. Again, we're just plugging in where the x is in the original equation. And we get -36. So 1 and -36. Well, that's going to be way down somewhere here. So it keeps going down. At some point, it's going to come up. Let's see what f of 2 says, which is in between. So I'm kind of taking the x's that are in between to see what happens. 2 plus 2 squared, 2 minus 3. And this one ends up being -32. So it starts coming up at some point. It might go farther down. We don't know, but it starts coming up here. Actually, it should be somewhere here, 232. And then it needs to come all the way up to 30. And remember, it's rising to the right. Okay, now we've got one more thing to do here, is use the fact that the maximum number of turning points of the graph is n minus 1 to check whether it is drawn correctly. Remember in the beginning, we said that n equals 3. So our turning points are going to be n minus 1, which is 3 minus 1, and that is 2. And if we look at, we have one turning point here and second turning point here. So we sketch it correctly, as accurate as we could. Okay, that's it for this lesson. Let me know if you have any questions. Bye.